now. All right, welcome back. We are GAME3001. That's Artificial Intelligence for Games in the summer 2022 semester at George Brown, and it's a week 11, part 1 of our broadcast and recording. And again, this semester is kind of weird. We start off with our lab recordings first, and then we do our lecture recording on Thursdays. So again, this is our lab 7.1 recording. So I'm going to start off with this and just talk a little bit about where we are. Last week we talked about state machines. We made a lab 6 was completed and due just this past Sunday. We created some path nodes and we created obstacles. When we moved the obstacles of the path nodes around, each path node had line of sight capabilities, and that's kind of a precursor to what we're doing this week. And it's something that'll help us with our assignment 3, which is kind of something we're starting off with. So that's lab 6 and state machines from last week. This week, what we're talking about is behavior trees, and I'll talk about lab 7. Lab 7 is a 3-parter, so it's worth 12% of your final grade. Pretty good in terms of pretty hefty in terms of weight. 1, 2, and 3 are all due on week 13, so that's a couple weeks out. So it's not going to be something that you have to worry about right now, but we're going to start with a starter today. And what I'll do is every week we get together, so next week and the week after, we will kind of build on this lab 7.1 starter that I've given you. A couple of things to note is this week, of course, we're meeting remotely, but I believe, if I'm not wrong, next week when we get together, I think we're supposed to be in person. Is that true, guys? You guys meeting in person next week with Philip or no? Yes, I thought so. So because Philip's in person, I'm also going to do my stuff in person. So that way, again, we can meet and discuss stuff as well. I will be there both sections for section 1 and section 2. But remember, section 1 starts at 1 and ends at 3. Again, we might go a little bit overtime today, just warning you in terms of content. There's a lot today. And section 2 starts at 3 and goes to 5. But remember, we're not going to do that. We're going to stay section 1 and section 2 is going to start from 1 and end at 3. That's what we're going to try and do. And we're going to reserve 3 to 5 for any Q&A, right? So any questions and answers, problems that you're having with your assignments or labs, and those kind of things. We can do that either remotely, as an example, or actually physically in class together when I see you guys next week. Okay, so that's how we're going to do it. We're going to still have those hours. We're just going to spread them out a little bit. Okay, so that is what's happening. Again, we're sitting at week 11, and we're going to start doing our decision tree. Again, that's the solution we're suggesting for assignment 3. But again, for assignment 3, just to kind of go over this again and restate it, you can use any of the structures that we've shown you, whether it's decisions trees, state machines, or behavior trees that we're talking about this week. So it's up to you which one you want to implement. We're going to show you decision trees in the lab. Okay, so that's the thing that we're going to go with, but it doesn't mean that it's the only solution or the best solution. Okay, so that's what we're doing. In terms of what we're doing today, we're going to download the Lab 7 starter, and we're going to go from there. So let's add let's start with that Lab 7.1 starter. You can find the starter like always. If you go to Labs on the left hand, you can always find it here. There's the Lab 7.1 starter. So please download this. And there's also a set of instructions that I usually include for each part. So this is part 1, and this is actually Alex likes to do this, and I've kind of borrowed it from him. I think it's a good way of kind of going through the lab requirements and everything else. So here's the Lab 7.1 starter, and here are the instructions. And let's move through this to make sure we have, kind of a good pace that we want to take. All right, great. So let's download. I'm going to download it or use it just like you. So again, I'm going to bring up my labs. I have Lab 7.1 starter right here. There's the zip archive. So I'm going to copy this, and I'm going to go into what we've been doing so far, which is on desktop. And I'm going to go into section 1 where we have our labs and paste it in. And then what I'm going to do is I'm going to extract it here just like I would expect you to do. All right, so then we can get rid of the zip archive. We don't need that anymore. And let's just rename this to Lab 7.1. You might want to rename it to Lab 7 because you're going to build on this one next week. Okay, so you're not going to just, there's no new starter. We're going to start with this, whatever we come up, the outcome from this week, we're going to continue with next week, unless otherwise noted. If I have another starter, I'll let you know. But for now, the plan is this is the one we're starting with, Lab 7.1. Okay? So hopefully you've had a chance to do that. And just like before, what we have is a Git archive. I'm just going to start off. You can do this with your desktop, GitHub desktop. I'm going to do it with command line. I find it a little bit faster and easier. It's up to you, however you want to do it. And I'm just going to, kind of go with this one and update the GitHub repository online. So again, it's git add dot, git commit -m, and we'll say added project files for lab 7.1 starter, which is what we did just now. Okay. And then git push up to GitHub. Now remember, this stuff, some people aren't taking advantage of the GitHub repositories that I'm sharing with you. So make sure for those people who are not sure where everything is, everything we talked about is up here on our GitHub for George Brown College, right? So if you look here, this is the one that I'm updating, and you can see here we have the exact same structure. So just a reminder, this is where you can find a lot of the code that we do together. Worst case scenario, you can always follow along and add your own stuff in, okay? Wonderful. So that's kind of a beginning for this piece, and we're going to continue to add to it as we go, okay? So that's where it's going to be. And of course, what I want to do is I want to kick this off. So let's kick off our project. So again, I'm going to go into lab 7.1 and double click on the SLN file, which should bring up everything that we need. Okay. And one thing that we want to do is when this comes up, we always want to test out our project, make sure that it's in x86 format like normal. And what we always want to do is test to see if we can actually run the project given. Okay, so please make sure it's x86, not x64 when you download it, and then run it and then see what happens. Does it run? Because if the project doesn't run, then there's no guarantee anything you make changes to from here on in won't have problems. So that's the first thing you want to do is make sure your project runs. Remember, I'm using Visual Studio 2022. Some of you have had issues with running Visual Studio 2022 for some reason, and that's perfectly fine. But what I'm trying to show you here is that there are definitely, ways of making this work. So here you can see that is a little different than what we've done in the past, okay? We have a bit of a background. Alex actually provided this background last semester, which is pretty cool. There's also some music that's attached to this whole thing. And I'll turn the music on so you can hear it as well. You should be able to hear it for yourself. But let's turn on, let's share sound. So there it is. So that's the music. Hopefully you can hear that. And it's just basically some music that we borrow from Star Trek 2, The Wrath of Khan, which is pretty cool. And this is kind of where the design of the ships come from too. This is the Enterprise and this is the NCL that we use. And it's kind of another smaller ship. And this is kind of in many ways maybe not proportionate because it's like this is a little slightly larger than this than what it's showing here, but pretty cool. Anyways, the great thing is what you get with it is you get a toggle the grid. Notice that the grid now is filled in, okay? And the other thing that you also saw there was that you also get, kind of like instead of obstacles being, kind of squares, which kind of ugly, now they're clouds. So if you run it again, you can see that the obstacles have just been replaced with kind of a cloud here and here. And they're just here for you to provide almost like the idea of nebula with clouds and all this kind of stuff, which is kind of what we're doing here, okay? So that's the starter. And anyone have issues with this at all? Let's start with that. Anyone have any problems running the starter? If you don't, check mark. If you do, X, have a problem. I'm saying. On this, I wanted to also mention, okay, just getting people starting it. Please get going on this one. Hopefully you guys are following along and got it going. Abu, are you doing okay? I can see that you haven't responded. And Zamarco too. And Jaden. And Fabian. I'm here for you guys. That's why we're doing this. So make sure that if you haven't had a chance to do it now, now's the time to kind of get it going. All right, a couple things to note. I have to mention this because there's a bit of administration before we start. So just going back to this for a second while you guys are getting to start this thing. Remember that each of these labs, they're all worth 4% of your final grade. So if you elect, for whatever reason, not to submit your labs, I mean, you got to think about what this means, right? So in terms of total labs, it could mean a big drop in your grade. So please make sure you submit your labs on time. Usually they're due on the Sunday. When they're due on the Sunday. There's no extensions and stuff like that at all. So we've given you a couple weeks. We work with you on them. And so they're a little bit different than assignments in terms of the way they're marked. Either you're on time or not. If you don't submit a lab or anything like that, you get 0. So some of the things that you don't want to do is you don't want to wait to the last minute to do this stuff. So work with me on it every single time we're together, so that way you're more successful and you have a chance to get full marks for this stuff. If you're someone who's been struggling, I'm just going to put this out there, and you have a problem with your, getting your labs out for whatever reason, technical issues, please see me after class, okay? Because I want to make sure that you have a chance, to fix this kind of problem. All right, but for now, we're starting off with this. And just like I said before, what I'd like to do is I like to get right into it and, kind of go through the labs with you. And there's always instructions. So let's follow the instructions together, which I recommend. So the first thing we did already, which was we downloaded our Lab 7 starter project, right? And so one thing to note is the reason why I gave you a new starter project, if you elected to try and work with Lab 6, the last version of Lab 6, there's a lot that we've added in here, okay? So, yep. Okay, Abu, let's talk after. So at the end of the day, what I want you to think about is when I give you a starter, it's because there's a lot of stuff that's been added to it, okay? So the first thing we want to do is what it says here. We're going to add in, because we're adding decision trees this week, we're going to start with adding decision tree filters. So that's the first thing. So here inside of the project, let's add, kind of a new filter as an example called decision. Okay, so let's do that. So right click on the template, and then we're going to add a new filter. So filters like a group or a folder, but it's not really a folder. So that's where it's going to go. And we're going to call this filter decision. Okay, let's do that. There's the decision filter. And let's do that inside here as well. Let's right click and we'll add in a new filter. Again, if you look at the new filter that we've added in, it's going to be actions and then agents. So let's do that. So remember, you can always rename them, actions. And then we're going to add a new filter called agents. Okay. We're going to keep going down here, conditions and core. So again, right click, add a new filter, conditions and core. This is kind of our starter, where we're starting off with the things that we're changing in our Lab 7.1 starter. Okay, this is kind of the first place we're doing it. And what it says here is in the core filter, there's a couple things. First, in the agents filter, let's move the starship .h and .cpp into here. Okay, let's do that. So again, starship is under game objects. So we're going to grab these two things, right? Starship.h and .cpp, and we're just going to drag and drop that into agents. All it does is just reorganize. It doesn't change anything. They're still located inside of the SRC folder, so that's nothing that's changed there. So that's where the first change. And next, we're going to go into, we're going to move the agent.h and .cpp into the core filter. So again, remember where agent is. Agent should be in core already here. What we want to do is we want to take it from the core application, and we want to move it into our core filter down here. So we're just going to drag and drop it from here down to here. And we're doing this so we can play with all this stuff if we need to right in here. Okay, so that's kind of what we've done so far. Okay, and that is the first thing. The other thing is there's a couple of files that I've included for you. So tree node, action node, and condition node. And those files are in the project, but they're not physically included in the files. Let's add them in right now. So again, and each of those should be put inside the core filter. So again, in core, right here, I'm going to add in an existing item this time, add existing item. And then under existing item, you're going to swim back to our 7.1 inside of SRC folder. Make sure you're in the right folder, as well as the project. You're in the right project. And again, what we want to grab here is tree node, action node, and condition node. So there's action node up here. And then condition node, we're going to control click condition node. So we get both of those things kind of selected. And we're going to scroll down all the way to get tree node, way down here to tree node. And we're going to drag in, or just notice there's three now, tree node, action node, and condition node. We selected all those by control clicking and then clicking add. And when we do that, you're going to see those three files, action node, condition node, and tree node. Those are the ones we've created. Okay, so those are the three kind of files we put together. And those are required for us to get going with. Okay, tree node, condition node, action node. All right, excellent. So that is the first part. And notice there's also an action state.h in Enums, in the Enums filter, right? And this will determine what action our starship is performing. And we're going to take a look at that in a second. So under the Enums filter, there is a new action state. And action state, there's different actions we can perform. And this is, again, helping you with your assignment 3. The attack action, the move to line of sight action, the move to player action, and the patrol action. So I'm setting this up for you to start off assignment 3 with, okay? And if we have this, then inside of our, the starship, the agent.h, I've modified agent.h for you. So if you look at agent.h here in core, here's agent.h, you can see that in agent.h, if you scroll down, there is an action state type, which is get action state. That is a method, as well as set action state. There's your getter and setter. And we also keep track of the action state now for all agents, right? Kind of that have it right here. So this is where it is right here. Okay, so action state is right here. And we've included action state because action state is just an enum that we're going to use later on. We can get and set action state for all agents. Okay, so that is what we've done so far. We've added some files. We've kind of moved some things around. No changes right now, but again, before we do anything, we should run it to make sure that there's no breaking code, and there isn't right now. Notice also that the grid, like I said, are solid rectangles as opposed to how we had them before where they were colored. And here you can also see that, like I said, the bounding areas of each of the clouds are just equivalent to where the obstacles were before. So if I move these around, you can see that that changes, if a node is visible or not, just like we had before, okay? So that's where we were in terms of the stuff we're doing. And this is a great place to put it up on GitHub. So I'm just going to go back to, you can go to GitHub Desktop, but this is a great place to do a commit. And we'll say added decision filters, which is really what we did right now. There's your commit. Okay, awesome. So this is kind of what we did so far. Also, some intermediate files got added to the template and so on. And that's the thing that we kind of did right there. Okay, great. So this is our starting point. And what we're going to do from here is we're going to definitely add more things as we go. And, the idea here is that we're going to make it so that it functions where the starship is going to patrol on its own, and it's going to hunt for the target, and the target being kind of our destination, our Starship Enterprise. For those people who like Star Trek, we're using that as a kind of as a motif here, a mode or theme. So again, notice that the target, it says target position, but it's this ship right here. Okay, so target position, and this is the enemy. So the enemy, and this is the target. This would be, your ship, typically your player, and this is the enemy. The enemy is going to try and attack you. Okay, so that's what we're working with right there. All right, so some changes to be made. So going back to our little instructions, we've kind of done all of this. And the next thing is, so we're going to prepare. And the way we're going to prepare is, and there's a bunch of commits. So one of them is, let's get all the action nodes set up. So remember that action nodes and condition nodes will make up the a part of the tree that we've talked about before. Remember, the top of the tree is the root, and then we have the left side and the right side, the left subtree and the right subtree. And there was a couple of lessons ago, we talked about in the decision decision tree lecture, which was week 9. So the week we got back from break. And I'm just going to bring up that PowerPoint for a second, just to kind of remind you of what we had done. At the bottom of that lesson, or kind of in that lesson, if I'm not wrong, I talked about some possibilities for, let's see if I can actually bring it up here, some possibilities for our, what our nodes would look like. So we kind of came up with a plan. So I said, like, the plan for, kind of what these things should look like something like this. For assignment 3, we're going to have a bunch of nodes, which is what you have. And then you have some obstacles, which we have. And then you have a base enemy class, and it's going to run around the screen and that kind of stuff. So that's kind of what we started off with. And then I said that what we can do is for the close combat enemy, we made a tree diagram. And the tree diagram kind of looked like this. In a second, I'll put it up. It kind of looks like this, where we have if the player detected, if it's true, then check to see if they have line of sight. So take a look at these conditions. Player detected, has line of sight. Are you close enough? Patrol, move to line of sight, move to player, and close combat attack are all the actions. So those are the action nodes. These are the decision nodes. Okay, pretty straightforward in terms of the way we've built our tree, the way it is right now. Okay, so this is the way we have it. We also had for the range combat enemy, we kind of extended that same idea. We talked about this if we're going to use decision trees. And we also included this idea of a health condition, the alarm, that we're going to kind of extend starting next week as we continue working with Lab 7. Okay, so again, this is that part. This is that tree I just showed you, but there's alarm conditions. And we talked about this last week when we talked about state machines, how sometimes there's an alarm condition that no matter where you are, it can kick you out of where you are and put you into some other state that you're going to be in later on. And we also talked about the possibility of combining decision trees with state machines, which is a lot of times maybe a good idea. For us, we're going to keep it simple, and we're going to keep it with a decision tree. But that's why we have these action nodes. So let's start with action nodes first. And the idea is we're going to define what these things are in actions. So right-click on actions. Let's add a brand new item. And remember, when you do brand new items, make sure you target the right folder. So it should be the SRC folder here, not the template folder. The template folder will go in the wrong spot. So you got to go browse. You're going to look in Lab 7.1 in the SRC folder here and click select. So your folder, target folder should be Lab 7.1 SRC. This is where it's going to go, just to make sure that you're in the right spot. We're going to click header, and in the header, we're going to start adding those actions. So the first thing I want to do is create the attack action or the patrol action. Let's say that's the first one is the patrol action. So let's do patrol action.h, all right? And we'll add that in. Here's patrol action.h. And what we want to do is immediately add in a new item called patrol action.cpp. So let's do that. So patrol action, and we want to switch this to CPP and add that into. There we go. In the CPP, what we want to do is immediately just include the patrol action .h. Okay, so that's the one thing I'm going to do right away. So that patrol action.h is here, and patrol action CPP is here. I'm just going to move them around so we can have this on this side first. For the patrol action, let's think about what this does. Again, what we want to do is, if not defined, we want to define a patrol action. That is the first type of action we can do, right? And we'll say we defined, kind of patrol action. This is our start. And again, we know that we're going to use action node. So let's include in here action node.h. Action node.h is, remember, if we look at action node.h, action node.h is a core, file we've added in from before. Let's take a look at action node.h and see why we're adding this in. So what is an action node? Well, an action node, right, is inherits from a public tree node. Okay, what is a public tree node? I'm going to come back to this. What is a public tree node? Go to definition, right? Go to definition. And if you look at tree node, this is what a tree node would look like. So remember, tree node is how we're going to build out a tree. A tree is a series of tree nodes starting with the root node. All right, so again, back to our diagram. If we're going to pull up our close combat enemy diagram here, let's take a look, right? That means each of these little boxes are tree nodes, starting with the top, right? So the player detected is a condition node. This is an action node, okay? And so, but what is a node? So the tree node itself starts off, the tree node class, it's an abstract class. Why? Because we have a virtual destructor, right? That's what we have. We also have a couple of properties. One of them is, and they're all in the public space here, and it's a struct, not a class. So it's a very simple structure is what it is. The tree node itself has the left tree node. There's also the right tree node, and then there is a parent tree node. So what left, right, and parent. So if I go back to the diagram that we have here, let's go back to that diagram for a second. You can see that if this is the root tree node, then it doesn't have a parent, but it has both a left tree node and a right tree node that would be connected to it, almost like a connection to these two things, okay? So that's what it would be. That's what these things are. They're pointers to other tree nodes, which means they are just connections. They're connectors, okay? And also, by default, we can classify a tree node as a leaf or not. Leaf nodes are the bottom part of the tree. Leaves do not have children, okay? So leaves don't have a left child node or a right child node. And you can see that these ones here, these action nodes, have no children, so therefore they would be considered leaf nodes. Okay, so that is the tree node superclass, and it's an abstract superclass because of this line right here, okay? All right, cool. So that is, what it is. Actually, it's more of a super struct more than a superclass. All right, cool. So then we can also inherit from structs, even though this is a struct, the tree node was a struct. Action node, which is what we're talking about here, is a class, and classes, difference between classes and structs a lot of time is just semantics. And what I mean by that is that by default, if they're public or private, by default structs are public, so you can access all of their properties, and by default classes are private, right? And if you notice here, we have a private section and a public section. The public section gives us the constructor function for this one, which is an agent, and we kind of initialize agent as a null pointer, and we also classify that all action nodes are leaves, right? So m_isLeaf is true because remember that action nodes are simply the bottom part of the tree. So these are all leaves, right? So they don't have any children. Okay, that's number one. And also, the action node superclass is a abstract superclass, right? So that's one thing to note. We also know that we have a virtual void action. So this here is a method that is an abstract method, which means we must override this method if we inherit from action node. So all action nodes have an action that they're going to perform. Example, patrol is going to perform the patrol action, right? And so on. And they also have a reference to an agent that they're storing. So an agent they're related to. So remember, whenever we create a decision tree, it's linked somehow to an agent. In this case, our agent is the starship. Okay, so the starship is going to have its own brain eventually that it's going to run around with and make decisions with. That's what it's going to be. So that's what the agent's pointer is. It points to the agent that this decision tree is linked to. It's important to do that. We can set agent and get agent, and we can store the agent here. So that is action node. So therefore, going back to patrol action.h, we are going to inherit from action node. So class, we're going to say patrol action, right? And that's going to inherit from a public, right, action node class. And that's why I kind of included it, because we're going to need it. So here we're going to make the constructor, declare the constructor for patrol action, as well as a virtual destructor. So virtual destructor means, because we're going to make other kinds of potential patrol actions. So we're going to say patrol action. There's the virtual destructor for that one. And we're also going to mark the action, there's our action, as something that we're going to override. So that is the override action. Remember that because patrol action inherits from, that's what this little colon means, patrol action inherits from a public action node, then we must override this kind of method that we defined inside of action node. Again, going back to action node, you can see that this must be overridden because here, this thing here is a abstract method or function. It depends on how you kind of, the language is different across different languages and different people say different things. You could say method because it's part of a class, or function if you're more comfortable with that. So it's an abstract method, and this here is an abstract class. Some people also call it an interface, but at the end of the day, really, it's an abstract class because, so let's just call that what it is. This is an abstract class. And the abstract class means that you cannot inherit, you cannot instantiate an object of type action node directly, as an example, because it's abstract. Okay, so action node needs to be something that you're going to inherit from, and you're going to create something more specific like a patrol action. So now we've kind of defined the patrol action, and we're going to put this in the public space, right? We're not going to define a private area because there's no private area here. And this is our .h for this one. And what we want to do is in our patrol action, I want to define all of this. So going up to this, I'm just going to use our ReSharper C++. So we're going to generate definitions by declarations, which is going to pull up a little bit of a dialog box. And I'm going to click finish, which is going to generate these stubs inside of the patrol action.cpp. Okay, so there's our patrol action.cpp. And what we want to do here is we're going to say m_name. We're going to give this a name. So define the name. And we're going to say that the name is patrol action. So there's the first thing we're going to do. Our patrol action is also going to have a default destructor for now. That's what we're going to do. And then the action itself is we're going to check. We're going to say we're going to say get agent, get action state, right? If it's not equal to action state, the action state dot patrol action, if it's not equal to this, right? Then what we want to do, by the way, notice that it says action state patrol. Well, there's a problem with action state. Let's go and fix it. Okay, let's talk about enums for a second. So enums can be written in a couple ways. One of them is they can be written like this, okay? Or you can make them into an enum class, which is also always recommended. So please make sure you change your enum for action state to an enum class. An enum class is safer and there's no difference. It's just that when you create it, you need to explicitly use the action state keyword, the action state name, almost as if this thing is inside of a namespace. So that's the only difference. So we want to add class into action state. And if we look here, you can see now that that is lit up. It's not something that we are assuming. There's no inference here. We know that it's the action state patrol enumeration, and patrol means value 3 in this particular case. So here we're going to put a standard cout. Whenever we do a standard cout, we know we're going to need to use the IO stream, right? Include right here. And we're going to output what this thing is doing. It's going to say something like performing, and then the name of the action we're going to perform, m_name, right? And it is a standard kind of output. And we're going to say get agent, and we are going to set the action state to the action state patrol action. There it is. That's the state we're going to make. All right, so that's all we're going to do right now. We're going to set the state to this. And that, my friends, is the patrol action. So whenever we get to the patrol action, because action is an action node, it's going to be different than a regular tree node. Let's look at tree node for a second. It's going to be different than a tree node. Tree nodes, right? They have left and right and parent, right? So they are tree nodes. That's what action nodes are. But they also have a specialization called action. This is the specialization, right? So the reason why I'm saying it's a specialization is because they are action nodes. All patrol actions are action nodes. And because action nodes, right? If I go to definition, because action nodes are a tree node, then the action itself, this abstract method or function, is a specialization. So remember that all child classes are fatter than their parent classes. So this is a tree node, but it has extra stuff on it, which makes it more specialized and fatter than the tree node in terms of its memory footprint. Okay, that's what it does. Okay, but further than that, if we go and define a specific action node, right, because action node itself is an abstract class, we need to specify a specific action node, which we have in patrol action. Therefore, we need to define the specialization. We define it here. Define here, right, kind of thing. So that's the specialized action we need to define. Every action node will have an action method, right? And this will be easier for us to see later on when we use it. Okay, that's the patrol action. And let's put this up on GitHub because our patrol action is now complete. So again, 2 parts to it, .h, which is this, and the .cpp, which is this. Are you with me? Check mark if you're with me, X if you're far away and don't know what I'm doing or you're confused. Ali is good, Jaden is good, Samarco is okay, Yigit is good, Vander is good. Awesome. Thank you. Abu, how are you doing with this? Are you with me? Thank you. Please use a check mark on the on Zoom to let me know. All right, next time. Thank you. All right, so let's move on from this. So now that we've got all of this, let's do a couple of things. We know that we need to add in a couple more of these things. So it says, look, we're going to add in all the action nodes. And the action nodes are going to be the attack action, the move to line of sight action, the move to player action, the patrol action. Those are all the action nodes we're going to add in. Now, quick way of doing this, instead of me doing all this work that I just did, let's, if I was to go to the template itself, and I want to show this thing in Explorer, open folder in File Explorer for a second, we can see that this is the folder for Lab 7.1, if you didn't have it open already. I want to go into the SRC folder, and because we already have our patrol action, let's just copy paste that one a bunch of times, because I don't want to do, it's almost going to be identical for all the other ones. So here's my patrol action, there it is, right? And I want to copy, paste. And when I do that, I have patrol action copy, patrol action copy. Let's rename these patrol action copies. So instead of patrol action, on the CPP side, it's going to be called, the first one will be attack action, attack-action.cpp. And we'll do another one. So patrol action copy, we made that patrol action copy right here, .h. We'll call this the attack action .h. Okay, so now we have two new ones, the attack action.h and attack action.cpp. All right, let's continue with this. I'm just going to copy paste again. So I'm just going to take these two this time. Doesn't matter which ones because they're the exact same as patrol action for now. And they're not included yet in our project. We're just copy pasting here to save some time. So Control C, Control V, copy paste these ones. So it creates copies of the files. So they're identical inside, but on the outside, they're going to be named differently. This is going to be called the move to line of sight action.cpp. Move to line of sight action, and this will be the move to line of sight action.h. Make sure that they're spelled correctly. Okay, make sure if you made a mistake spelling these two things, you can also copy paste that, but you can see that all of these things are spelled in identical ways. Okay, so there's not a problem here. So that's the move to line of sight action. So far we've added the attack action and the move to line of sight action. Let's add in the move to player action the same way. Okay, so because this is already called move to something, this will be the good one to copy paste. So copy paste, and we'll call this move to player, right? This is where the close combat move to player action, there it is. And we want to change this to move to player action, move to player action.h. So we have all those, .h and .cpp. So we've got move to player action, we've got move to line of sight action, we've got the attack action. Those are the new actions we've defined. We only have the patrol action inside here. Well, we can actually include all the other stuff. So let's add it, existing item this time. So this, we can do this, and we can add those in. So again, the attack action, there it is, and the attack action.h. We also have the move to actions. So move to is down here where we can get the move to. I'm just control clicking here to get all of these in here. There's the move to line of sight, move to player, right? And that gives us all the actions. You can see them all listed here. And if I click add, it adds all those actions to my filter. So they're just copies of the original thing. Okay, again, you could do this in different ways. This is just one way that I figured out that I would do it. Let's start modifying the attack action. Okay, so the attack actions. So the attack action is clearly not going to be called patrol action. So let's rename anything that has patrol action to attack action. So again, up on the top here, we want to rename this to attack action. Okay. And I'm just going to copy paste these little things here, right? So that way it says all the same things. There's attack action, right? I'm starting with attack action. And now I'm going to Control F. So Control F, I'm going to search for the patrol action. There it is, patrol action. And I'm going to replace it with the attack action. So nice and easy, we're going to do that. And I'm going to replace all. So those are all the occurrences in this file. So all the occurrences have been changed to attack action. And for the most part, this is identical to the patrol action. There's no difference here. Okay, so that's attack action.h done. We just renamed stuff from patrol action to attack action. Next, the attack action.cpp, there are some changes. Okay, when this is where the changes come into play. So first, again, we want to rename anything that has patrol action to attack action. Let's do that. So Control F. Again, we're looking for patrol action and we're changing it to attack action. Replace all, please. And when we do that, you can see that it's all been replaced to attack action. Okay? Attack action. However, right? So you can see here that this is patrol action. We're going to change this little name to attack action if we ever need to do this right now. Okay? Everything else stays the same except for our action state, which goes to attack. There it is. And of course, we're going to change this to attack here. Okay, so that's what we're going to do right away. So that's the only difference between one type and another. So for now, all it's doing is just setting an enumeration. That's what the action does. It basically says, hey, just set the state. We're going to keep the state for that particular action in the agent that we've attached things to. We're setting that to this action, whatever the attack action is. So we're going to just keep the state in the brain of the agent. And that's what this does. When we're in that particular state, the agent is going to perform that particular action. That's how it's going to go. Cool. So that is attack action done. .h, just renamed. .cpp, just renamed. Copy pasta. All right, that's what it is. There we go. Let's move on to the next one. So now that we've got our action state, let's do move to line of sight action. Again, we want to rename, so Control F. We're searching for the patrol action, action, and we're renaming it to the move to line of sight action. A bit long, but it's okay. Move to line of sight action. And we're going to rename all. There we go. Excellent. We also have to change this one. So this is move to line of sight action. And usually what we do is we do this, move to line of sight. So spaces between the names for the words. Okay, something like this for the definitions. So for the guard function, move to line of sight action, right? And that's it for the .h. So this is pretty simple. And I'm sure you're going to fast forward faster than me. And then let's get into the .cpp to fix that one. So .cpp, just like we did before, we're just going to rename everything there. So Control F, we're going to search for a patrol action. And we're going to replace with move to line of sight action. Replace all, please. Okay, there we go. This is nice and easy to do. And again, this will be called the move to line of sight action when we output it to the console. And the action state is going to be move to line of sight. We're going to detect if it is, and we're going to change it. So this if statement, basically, we don't want to keep changing it to move to line of sight. So this checks to see if it's already there. And if it's already performing move to line of sight, it's not going to spam our console with move to line of sight nonstop. So that's what this little thing does. All right. And our move to line of sight action is done. Finally, let's do the move to player action. So close this off and go to move to player action. And let's rename this one. So again, let's start with this part up here. So move to player. So move to player. Again, just renaming the if not defined statement here. Okay. And again, I'm going to Control F. By the way, if you want to be smart about controlling F, if you double click on something and then Control F, it'll pull it up here. And then you can say, I want to change this to move to player action. Move to player action and replace all. We'll replace everything that's in here. Nice. That's done. Move to player action. And we'll do the same thing with our move to player action.cpp file. So move to player action CPP. Let's double click on the patrol action and Control F, where we want to change it to move to player action and replace all. Nice. And make sure this is also move to player action, which is the action state that we're changing to. Okay, there we go. So that's move to player action done. And my friends, we've done all of the action nodes. Now you might say, well, like, these are kind of useless, but they're kind of like interfaces is what they are, right? So that's what they are. Let's put this up on GitHub because that's what we've done. So we're going to go here and go clear. We're going to say git add dot, git commit -m, and we'll say added action nodes. Git push. Okay. So those are the attack action, move to line of sight action, move to player action, and patrol action. Those are all the nodes. And if they match with our diagram, which is this, patrol, move to line of sight, move to player, and the attack action. Okay. Nice. Now we need the condition nodes. We're going to do that next. So let's get the condition node started. It's going to be the same process and some copy pasting involved. So let's close off, let's save all, close these off. Nice, nice, nice. And what we want to do is we want to go into conditions, and we're going to add the first one. So the first condition, we're going to add it in by hand, new item, and it's going to be a .h file, okay? And the first condition that we're going to add in is the line of sight condition. So it's going to be called the line of sight, LOS, condition.h, line of sight condition.h. Okay, it's going to go in the SRC folder. We're going to add that in. There it is. And we're also, at the same time, going to add in a new item called the line of sight condition.cpp. Line of sight condition.cpp. And then click add. And here, immediately what we want to do is we want to include the line of sight condition.h. There we go. In the CPP. And in the .h, we want to talk about the line of sight condition, right? So we're going to say if not defined, and it's going to be the line of sight condition. How about if I spell it properly? Right? That's the line of sight condition, and then we're going to define the line of sight condition, and we're going to do an end if, excuse me, and it's going to be defined line of sight condition. Okay. And in here, what we want to do is we want to include the condition node .h. Uh-oh, that's a new thing. And let's talk about this before we continue. What is condition node .h? So condition node is very similar to action node. They're both tree node types. In this case, a condition node, the leaf is false. And the reason for this is because leaf nodes do not have children, right? They do not have children here. You can see there's no children for patrol or move to line of sight, move to player, or close combat attack. However, the condition nodes must have some kind of children. So you can see there's a child here and a child here. That's the difference. So condition nodes cannot be leaf nodes. They cannot be leaf nodes. Back to this, and that's why this is defined. The condition node leaf is defined as false, this struct, or this class. And we also have a virtual condition node, and this again is an abstract superclass. Abstract class is what this is, right? And what we're doing here is we're defining the condition. So here is the condition specialization, which is specializing what the tree node would do. So it is a tree node. It has left and right trees and all that stuff, but it also has a condition method that we want to override. That's what we're going to do here, okay? So that is what a condition node looks like. It's a little different than an action node in that conditions only have conditions. They don't have actions, but they're still tree nodes, and they have children, a left node and a right node. Okay, cool. So this is my condition node, and how does this look? So I'm going to say class line of sight condition, right? Inherits from a public condition node. There it is. And what we want to say here in the public space is that we have a line of sight condition constructor, which is going to take in a Boolean called line of sight, which is going to be initialized to false by default. Okay. We also going to make a virtual destructor, right? And then we're going to have some getters and setters. And the one we want is a void set line of sight, where we want to set the line of sight. Do I have line of sight or not? Okay. And then we're going to have a virtual Boolean condition as an override that's going to override the condition method that is specified inside of the condition node superclass. Finally, we will have a private method, private section of our interface here, and it's going to have a Boolean m underscore has line of sight that we're going to keep track of. So that's what this is going to do. And that is, my friends, is the line of sight condition.h. So a little different than what we saw before. Okay, just like we did before, what we want to do here is we want to click on the line of sight condition, go to the little light bulb, and go to generate definitions by declarations, which is going to create this all the stubs that we're going to have inside of line of sight condition.cpp. Let's finish that and see those stubs. Wonderful. So line of sight condition.cpp then is going to have a couple of things. One of them is going to be the name. M_name is equal to the line of sight condition. So that's the first thing, okay? And that's the first part we want to do. We also want to set line of sight to whatever we pass into the constructor function. Since this constructor function is getting a Boolean by default for all line of sight conditions, this could be considered const, and we can change that to const here. So it's a const Boolean called line of sight. Nice. In our destructor function, we're going to set it to default, as we've done many times in the past. And our void line of sight condition set line of sight, we're going to set the m_has line of sight property or private property, private instance member to whatever the state that we pass in, which makes it so that we can make the state const as well. And finally, when we return line of sight, when we actually define the condition, we're going to say that we want to return m_has line of sight. So that's what the condition is going to do. It's going to return, do we have line of sight or not? And that is our first condition node defined. Okay, line of sight condition. Okay, so on this one, because this is where we're going to start, we're going to do some copy pasting again from here, because we got a close combat condition. We also have a radius condition. We have those two as well, right? Are you with me? Are you with me on this one, on line of sight condition? Check mark if you're with me. If you're not, I'll wait, because I want to make sure you guys are good with this. Yigit's good, Vander's good, Abu is okay, good. How about Ali or Fabian, Jaden, Michael, Samarco? Are you guys good yet? Okay, so that is the first part. Thank you for that feedback. So this is good. And now that we have line of sight condition, we can close this off, and we'll do the same trick we did last time, which is, let's go back to our src file. And again, you can open it up if you already had it open. And what I want to do is I want to go to that line of sight condition, which is right here. Here's our line of sight condition. And I want to copy paste a couple of times. So let's copy the first one, copy paste. And we're going to call the first one a close combat condition. Close combat condition. So this is going to be called the close combat condition.cpp. And this will be called the close combat. By the way, if you're worried about spelling and you need to get this right, you can always just copy this one, this part, close combat condition, and just go back into that copy area and just paste it in, right? So that will spell it properly for you. So there's the close combat condition.h and .cpp. They're spelled the exact same way. And the next one is the radius condition. So let's just copy paste this one. Doesn't matter which one. Copy paste. And we want to make the radius condition. So I'm just going to rename this to radius condition. Radius condition. And this will be again the radius condition .cpp. Radius condition. Again, make sure you spell it correctly, guys, and you do the right thing when you're renaming, because this is where people get into trouble. They rename it wrong, and then they got problems. Okay, so there we go. So there's the radius condition, and we also added the close combat condition. Those are the two conditions. And again, if we look at here to see our diagram, we have a line of sight condition, we have a radius condition up here, and we have a close combat condition here. So those are the three conditions. We only have three conditions, and those are the ones we're defining. We're just calling them different things. And let's move them into our conditions filter. So we're going to add existing item, and we're going to go to you do it in reactions, Fabian. And we're going to add those in. So we're going to add in the close combat condition as well as the radius condition. Those are the two that we're going to add in. So let's get the radius condition in there too. We're just control clicking so that we have everything in here. Okay, so if I click add, you can see now we have all of those. There's 3 conditions. And what we're going to do is just rename them and readjust them as we go. So first we'll start off with the close combat condition. Close combat condition is lots of changes here, but let's start off with renaming. Okay, so close combat condition at the top, we'll call it close combat condition. So close combat condition, because this is the close combat enemy that we're creating. There's close combat condition, right? And again, we want to kind of rename this part right here. Good. And we're going to double click on line of sight condition, Control F, and we're going to expand this, and it's going to say, okay, so the line of sight condition is going to be renamed to the close combat condition, right? Rename all. There we go. So that's the first part we need to get right, close combat condition. Now, so getters and setters is different. So this is where we get a lot different stuff. The condition stays the same, and this changes. So private M underscore has line of sight is going to change to M underscore is within combat range. That's the name of the private Boolean, is within combat range. And instead our getters and setters being set line of sight, we're going to set is within combat range. So that's the only difference between one and the other. And so this is where we're going to make some changes. It's not exactly a copy paste operation, but there's some stuff we can do to save time, which is what we've done. So save close combat condition. So close combat condition is different because it has different getters and setters as well as a different property here. Okay, so that's one thing to note. Let's go into close combat condition.cpp. So again, what we want to do is we want to double click onto line of sight condition, Control F, and scroll down to change it to close combat condition, rename or replace. Now this is where we get into some interesting stuff because we have close combat condition line of sight, but that is not correct, right? Even here it's not correct, line of sight. It shouldn't be here. It should be renamed to something like within combat, this is in the .h, range is equal to false, within combat range. And in the CPP, it should be the same thing. It should be within combat range. So that's also different, right? Again, we're just trying to save time so you don't have to type everything by hand. Set line of sight doesn't exist. It's got to be set is within combat range, and we're going to put in within combat range as a parameter. There we go. The set line of sight doesn't exist. This is actually called set is within combat range. That's what it's called. And instead of updating has line of sight, we're updating M underscore is within combat range. And we're going to return the same value out in the condition node. And that is the difference between line of sight condition and close combat condition. Save. So those two things are done. You can see that those are ready to go, and we can close off this one. Next, let's do the next one for radius condition. So radius condition, again, we're going to double click on line of sight condition, Control F, and change this to radius condition. Did I? Okay, I'll go back to that in a second. Sorry about that. Let's do that before I forget. So you get was saying that close combat condition.cpp, I forgot it. The line of sight condition should be called close combat condition. Thank you for that. Close. This is what happens when you copy paste. You make mistakes, right? Save. Thank you for that. All right, good. So let's go back into the radius condition. We've changed these, but the radius condition is slightly different as well because Well, it's the radius condition is here. This will be called radius condition. Radius condition. And here too. So radius condition has been renamed, but this is no good. This is going to be renamed to, so we're going to rename, so refactor, let's do refactor rename. We can also do that too. Refactor rename to a set is within radius. Set is within radius, which is what this thing should be called. Set is within radius, okay? And that's the condition. Instead of this, M underscore has line of sight, M underscore is within radius is what the method, the private member is within radius, right? And now the .h is done for our radius condition. Awesome. There's our radius condition done, okay, for the .h only. Let's do the .cpp. It needs a little bit more love than this one. Okay, so again, .cpp, double click on the line of sight condition, Control F. This will be called, so we're moving to radius condition and replace all. That's the first step. And just because you mentioned it last time, I don't want to forget, let's just rename it to radius condition. And set line of sight is not going to be called set line of sight. It's set is within radius, and it's not going to be called line of sight here. It's going to be within radius. Go, and this is not called set line of sight, but set is within radius. And then we're going to change the M underscore is within radius instance member and return it out. And that is your radius condition done. Your radius condition is over, right? So that is everything. And it's exactly the same for the most part as the other ones with some minor changes. Okay. Excellente. We're good to go. The constructor parameter. Did I miss something? Oh, no, we're good. I think we're okay. Then what does this say? It says rename the parameter within radius to line of sight. Did I change it to here? Haha, within radius. Thank you. Awesome. Nice. And we've done everything. Thank you for that. And that is all of that done. Let's put this up on GitHub because now we've finished off doing our condition nodes. Git add dot, git commit -m. We'll say added condition nodes. Git push. Wonderful. So that is that all done. And we're ready to go. We've done all of this. And if we look at our instructions, we've done all of the action nodes, all of the condition nodes, and now the big step, which is getting that decision tree defined. So we have to make the decision tree class from scratch, which we don't have. And we're going to start talking about how this is going to go. Notice it says this is going to take a long time. We're sitting at 209, my friends. It's going to take most of the remainder of our time together. Right here, okay? Let's make sure this works. And we're going to get to it. So the decision tree class itself will go into the core filter. So again, we have actions, we have agents, we have conditions, we have core. And in the core filter, we're going to add a brand new item. And the new item we're going to add into the .h first is going to be called decision tree. Okay, so we're going to actually define this data structure now. Okay, decision tree .h. So let's add that in. And at the same time, let's add in a new item, which we're going to add into the .cpp called decision tree.cpp. Decision tree.cpp. And we're going to immediately include decision tree.h, just so that way that is ready to go. In our .h, just like we've done in the past, we're going to define our if not defined, this is our guard decision tree. So this is a decision tree data structure that we're making now. So first data structure we've kind of done beyond the regular ones is this one. Oh, okay, pretty straightforward. We know we need to make a new class called decision tree. It's not going to inherit from anything because this is a brand new structure, our data structure that we're going to make. We have our public area and we have our private area. And in our public area, I'm just going to start outlining what I want to do. I want to define some constructors. We want to define a destructor. We're going to define some getters and setters. I'll spell that in a second, which are like accessors and mutators. Okay. Okay, so this is just outlining. All I'm doing is outlining. We can go to make some public utility, or we like to call them convenience methods. Okay, that's what those are. And in the private area, we're going to have our private data members, also called fields. Okay, that's where they're there. We're going to define a tree node list. We need to do that, as well as some private methods that are only going to be used by the class itself. And that is our beginning structure. We want to start always with some kind of structure, almost like a map of how we're going to organize our code as we start off. Okay, so this is kind of where it's going to be. And what we want to do here is, just like before, we want to define a couple of constructors. Let's start with those. So again, decision tree is the basic empty constructor. So this is the default constructor, right? We also want to define another one, decision tree, but this one is going to take an agent pointer. So agent. And notice that it's asking me to import stuff, and we're going to import the agent class, agent.h. These are the imports. I'm just going to make a space here. So that's our constructor. Our destructor is pretty simple. Oh, yes. Getters and setters. So things we want to be able to do, because we are defining an agent, we need to store the agent somewhere. So that's one of the first data members we're going to have. We're going to store an agent pointer called m_agent. So something that the decision tree is going to be connected to, some agent that it's going to be connected to. That's what that's going to be, almost like a back pointer to the agent. Okay. Well, if we have agent, we need both getters and setters for it. So let's do a get agent and set agent. So we're going to do the getter first. We're going to say agent pointer. We're going to call this get agent. And it's going to be a const type, because it's going to return one thing. And we're also going to set agent. So get and set agent. And of course, we want to set the agent pointer that we're pointing to. So this, again, is some regular stuff we have done in the past, right? Yep, it says we should mark it as no discard. I'm just going to do this so that it is modern. No discard is double brackets. This is for the compiler. It's happier this way, as an example, when we do a no discard, okay? And yep, it's good. So we're good to go here. So that is the getter and setter. Getter and setter. We also want to get line of sight, and we want to get the radius node, and we also want to get the close combat node, because a lot of those things we want to be able to, we want to get access to those decisions, right? So we're going to say line of sight condition pointer, right? Line of sight condition pointer, and it's asking us to pull down that. So there's our first one, line of sight condition. We just made that. line of sight condition pointer is we're going to get line of sight node, whatever that is, right? And we also want a radius condition pointer. It's asking us to import that. There's our radius condition right here, we just defined. And we're going to get radius node const. And the close combat condition pointer, it's asking us to import that as well. Let's do that, import that. And we're going to get the close combat node. And these are just going to return references to the nodes we're going to add into the, to the tree as we build the tree structure. Okay. In our public utility method, we're going to add a tree node. We're going to have an add node method, so we can add nodes to the tree. So what we're going to be able to do is construct a tree by using add node. Every time we use add node, it's going to add a node to the tree. And the add node function is going to be very special. So tree node, it's going to return a tree node pointer, and it's going to say add node, and we're going to have, it's going to take in a tree node, which is the parent, right? A tree node, which is the child node, right? So that's one thing we're going to be able to do. What's the child, if anything? And the other thing is we're going to add in the tree node type, right? Tree node type is also what we want to add in. And you can see that we have tree node type that I've included for you, tree node type, right? And tree node type is the type. So remember tree node type, if we go to definition, what that is either the left tree node or the right tree node. That's the tree node that we're going to add in. When we add a new node, is it the left tree or the right tree? So going back to our diagram, if I construct my diagram and I say, okay, so patrol node, right? The parent would be the radius node, right? That's the parent. And is it the left node or the right node? Well, we're defining it as the left node. So this is where it's going to sit. When we traverse the tree, we're going to put it here in the node itself, okay? So that's what the tree node, this add node is going to allow us to do, identify where in the tree this node is going to be added. We're adding it to a position in the tree itself. Next, we're going to have a display function. We're going to have a update function, and we're going to have a clean function. We're also going to have a make decision function that is going to perform in-order traversal. Okay, so in-order traversal goes from the left to the right, okay, as an example. And that is the first part of our decision tree.h. We're just defining the stuff that we need in the interface, okay? The tree node list down in here, we're going to get to this, but here inside of, if I'm going to return, look at this, if I'm going to return line of sight condition, radius condition, and close combat condition, well, I might as well have those private data members here as well. So kind of a list of those things. So line of sight condition pointer, it's going to be m underscore line of sight. We're going to call this line of sight node. So this is kind of more of a specialized tree. It's not a generic tree structure because we're returning very specific things. Okay, that's what we're returning here. So line of sight node. And our radius condition is m underscore, we'll call this the radius node. And our close combat condition pointer is going to be m underscore close combat node. All right, so those are the nodes. We're going to keep track of all those nodes. They're very special nodes we need because those are all the conditions in our tree, in our specialized version of a decision tree. Okay, that's what we're doing. It's not as generic as we could have made it, just to make it simpler. And we're also going to have a vector of type tree node pointers that we're going to call m underscore tree node list. Okay, so we want to keep track of all the nodes inside of the tree, And so if I need to do a traversal or a removal or something like that, or a printing, I can do that much easier. One thing you can see here is that I have not included the vector so far, and we could, but remember that up here we have tree node type as an example, right? We have tree node type. And we also don't have a reference to treenode.h. I think it's a good idea to include this too. So let's include treenode.h just to make sure we have it, right? We probably don't need it because we have it in here in these ones, but it's okay if we include it just in case. We have agent, close combat condition, line of sight condition, radius condition, tree node, and I probably want to include a vector. So the reason why I want to include vector itself is why? Because we're using vector here, right? So just in case it has a problem doing it, we'll have the definition for it. It probably won't because we've defined it other places. And finally, we're going to have in our private methods a void m_build tree. And build tree is actually going to build the tree up. That is the method that we're going to use to have all of this stuff built. Okay, so that is our .h for the most part. Any questions? Are you with me before we save it and move on to the .cpp? If you're not ready, please indicate that. If you want me to wait, I will wait. If you're ready, I'll move on. Thank you. You get Vander, I got Jaden, Ali. How are we doing? Abu, Fabian. Yeah, there we go. Ali, Abu, and Zamarco is good. So we're just waiting for Fabian and for Michael. All right, good. So that's good. Excellent. So let's save that. That's the decision tree.h. And just to help, what I'm going to do is I'm going to push this right now to GitHub. So git add dot, git commit -m, and we'll say added decision tree.h. This way you have the decision tree.h ready to be done. And you can always look up on GitHub if you need to get my code. So you don't have to wait for me to, you don't have to ask me to go back. All right, so now that we have this, we can go to the top here and we can say generate definitions by declarations. And it's going to have a pile of these method stubs that we want to add in. I'm going to click finish, and it's going to make all the method stubs appear in our decision tree.cpp. All right, again, I'm using ReSharper for this, so that way it does it. So ReSharper is pretty cool. Decision tree.cpp. Okay, so let's start off with the constructor function. So the constructor function, the only thing it's going to do is called the m_build tree method. That's the first thing it's going to do. That's the default or empty constructor. Okay. Now it also says that it says apply a clang tidy fix for CPP core guidelines pro type member init. And if I click that, then it takes away that issue. What it did was in the tree decision tree itself, it will initialize those members. So look at all these members here. They all got initialized. Curly braces initializes them all. That's what it wanted us to do. So that's what I agreed with. There's also another underline here. It says it's the default constructor. It says variable decision tree is uninitialized, always initializes member type. It tells us all this stuff here. These are all the things that we're going to do. But we're going to do that in the next coming part. Decision tree dot the second constructor. This is the second constructor now. For the second constructor, we're going to say m_agents is equal to agents. Yeah, this is the first thing. And m_build tree. Now, what we could do, because the only thing we're doing here is adding an agent, we could call the first decision tree method, up here. And this is the constructor function here, or not. It's up to you. I'm just going to keep it simple. For the decision tree dot destructor, I want to make this equal to default, like we've done before. And the getters and setters are pretty easy because we're just going to return m_agents for the get agents. For the set agent, we're going to say that m_agent is equal to agents. All right, so that's what that is. Pretty straightforward. For the get line of sight node, we're going to return m underscore line of sight node. For the get radius node, we're going to return m underscore radius node. For the get close combat node, we're going to return m underscore close combat node. It even recommends it for me. I don't have to even think too much here. And now we come to the meat of what this thing does a little bit more. So add node is the first function that is a little bit more meaty. Okay, not much, but a little bit more. We're going to make a switch case. All right, so switch case. And the expression that we're going to put in is the type. We're going to switch on type. So whenever we switch on type, we need some cases. So case is the left tree node, but we don't want this. Remember left tree node? We talked about this as a tree node type. Tree node type. Well, if I go to definition, we made tree node type just a regular enum. Please change this to an enum class again. So enum class is the tree node type. Tree node type. And what this does is for the case, we can say control space, we can say tree node, the left node, that's 1. And the other case is the right node, that's the other. And notice I just pressed control space to give me those recommendations. Right, left node or right node. Type says it would be nice if you made me const. That's what type tells us to do. So const type. Here the cases are something that we want to say. We want to say that if I'm the left tree node, then go to the parent node and indicate that m underscore p left, the left node itself, the left child, is equal to this child node. All right. And if I am right, then let's set up the parent. So m underscore p right is equal to the child node. So all we're doing is configuring which node, what's the parent of the node we're adding in. That's what this add node does. What's the parent? And then on that parent, let's define either the left node or the right node. Okay. It also says, gives some examples, it says add a return statement. So we're going to add, because that's what it's looking enough for us to return a tree node type. So we're going to do a couple more things. One, we're also going to configure the child node. We're going to say the child node's parent, m underscore p parent, is going to be equal to the parent node that we pass in. So this is kind of creating a backwards connection. So it's a two-way pointer. So one, we know the parent knows what the child is, and two, the child knows what the parent is. So kind of they point to each other. So we can always traverse one way down the tree or back up the tree if we need to. Okay. And then finally, we're going to return the child node. Okay, so we can always return the child node back out. Okay, and that is your add node method. There's still an underline. And again, I always like to look at these. It says, make function static. Nah, I don't think so. That is kind of an option because it's saying, well, you might as well because all decision trees will have the add node method. It's not specific just to one tree. So this is something you can make static that's available to all nodes. I'm going to recommend not. So I'm going to ignore this one. Okay, let's skip down to this part down here. Display. How do I display it? It's just going to be a way of us outputting to the console. So I'm going to say for each, and we're going to say for each node in the tree list. Here's the tree list for each node. For each node in the tree list. For each node in the tree list. What I want to do is I want to standard cout, and I want to take that node and I want to output the name of the node to the console. So we can say how it works. Now, cout requires a IO stream, which will take care of that. And now you can see at the top that we've included IO stream because of this little display method. Display is also underlined. If I go here and go to what it's asking for, it's make the function const. I'm okay with that. Okay, also here in the for each loop, it's telling me that this should be also const. There we go. So far, so good. Save. The update function. Right now, we don't have anything in the update function. This is going to be something in the placing. So do something in the placing. That's what's going to happen. I'm not going to put anything in there for now. So the update function is going to remain empty in here. In the clean function, this is the first time we're actually adding something in the clean function for a while. We're going to do a for each loop for every node in the tree node list. For every node, wow, in the tree node list, this will be called node. And what we want to do is we want to delete the node, and I want to set the node to a null pointer. So if I want to clean it up this way. I also want to say that the tree node list is going to clear. I'm going to shrink to fit the tree node list, which is going to shrink it back down to nothing. I'm going to set the line of sight node to a null pointer. This is just me cleaning up the pointers that we had in here. I'm also going to change the radius node to a null pointer. So just cleaning up some memory, and the close combat node to a null pointer. Okay, that's our clean function. And in the make decision method, we have two more to do: make decision and build tree. Build tree is where we actually build the tree manually, and make decision is where we actually make a decision based on us doing a traversal. So this is, again, we're going to traverse the tree in order. And if you ever look at in-order traversals, let's take a look at that. If I do an in-order traversal, what does that mean, right? So tree traversals, in-order, pre-order, post-order, right? So if this is a tree structure, there's a bit of a thing. In-order traversal traverses from the left subtree. As an example, you visit the root, and then you go to the right subtree. So what this means is, if I go to here, I visit this subtree, go to the root, then go to the right subtree, go to the left subtree, go to the root, go to the right subtree, right, as an example. And by the way, the right subtree, then I go to the left subtree, go to the root, and finally go back to the right subtree. So it kind of does that scenario. So left, middle, right, left, middle, right, left, middle, right. That's how it traverses through the tree. Okay, that's in order. Just to give you an example. Back to this. So back to this part. So now that we want to make that in-order traversal, how do we do it? So again, what we want to do is we want to put together our tree node pointer, which we're going to call the current node. And the current node is going to be equal to m_tree node list 0. So we're going to start off at the top of the tree. So the root node, right? Top of the tree is where we're going to start whenever we make a decision. We're going to do a while loop. And while not the current node, right, is a leaf. So we're checking that it's not a leaf. If it's not a leaf, we have more traversal to do, right? So while the current node is not a leaf, we're going to say, hey, current node, we're going to, we want to get the condition of the node itself. So we want to return whatever the current node's condition is. So current node, we're going to say current node condition. And the reason why we can't get this, it says, current node, we're trying to get the condition of the current node, but we don't have a condition, because nodes can be either a condition or an action type, right? However, we know it's not a leaf. We know that if the current node is not a leaf node, it must be a condition node, and therefore we should cast it as such. So we can do it like this. Typically, we would do something like condition node pointer, but resharper is going to tell us that this is ugly. And what we want to rather do is use a static cast to kind of call this function. So tree node has no member condition, it says. So, and we're casting this one. We're casting this one as a as the node itself. So this is the condition. So we're saying, hey, if the current node's condition is true, then what we want to do is we want to go to the right subnode. We're traversing, right? If the current condition, so if it's not a leaf, if we haven't hit a leaf, this is how it works. So we're at the top, we haven't hit a leaf. If the current condition is true, R is the player within radius, as an example. That's the top of the condition. If it's true, then go here. If it's false, then go here. So here we're going to say, if it's true, then we want to set the current node. We want to set the current node to the m_p right? Otherwise, if it's false, then we want to set the current node to m_p left. So how did I do this? Why did I break it out this way? This is a ternary operator. It can be written in one line like this. It's just easier for us to see it broken out like this, okay? Maybe in 2 lines. So static cast, it says static cast. It says, hey, replace static cast with dynamic cast. It says CPP core guidelines. When we downcast. Whenever we downcast, we want to use a dynamic cast, not a static cast. I'm okay with that. And that's what the recommendation is. Cool. So again, what we're doing is we're looping through the entire tree. As long as there's no leaf node, we're going to take the decision based on whatever the condition is, if the condition is met or not. So it means that, going back here, do I have line of sight? Yes. Or sorry, is the player detected? Are they within radius? Yes. Okay, do I have line of sight? Yes. Still not a leaf node. Am I within close combat range? Yes. Attack. Now I'm at a leaf node, and I break out of this while loop anymore. We're broken out. And once we're out of the while loop, whatever's left is the action node that I want to take. I want to take that action. So here's, I want to take the action. So take action. So I've bubbled down, or I've kind of navigated down the nodes. This while loop here is traverse tree down through each decision, right? And then when the decisions are no more, there's no more decisions because one of them happens to be a leaf. We get to a leaf. Now take an action. So because the current node would break out of the while loop, now we're an action node. So now we have to cast it as the current node is an action node we're going to take. So let's just be kind of in advance. We know we're going to have to dynamic cast it as an action node type. We can actually include it as an action node pointer. There we go. We can cast it, and we can say that the current node is an action node, and we want to take the action that is associated with it. For example, patrol or attack or whatever the action is that we're going to bubble down to. So we're going to bubble down to an action by traversing the tree. When the last decision is made, so again, it's the player's detected, no, patrol. So as soon as, if it's a false, and if it takes us into in this case, for this week, we're gonna go into patrol mode right away, right? You're gonna see if the player is not gonna be detected by radius, because radius is not gonna work, it's just gonna take us into patrol mode this week, okay? All right, so that's what this make decision does. Again, guys, we're running a little bit over time. Please bear with me as I build out my tree. So that is make decision. Make decision, if you notice, it says make the member function const. I'm okay with that. Save. And then finally, build tree. So we're going to have some conditions, and we're going to have some actions that we're going to build in the tree, right? That's the thing we're going to do. And the first thing is, let's create and add the root node. So this is all manual. So we're going to make our manual tree. So we're going to say m_line of sight node is equal to a new line of sight condition, where we're passing in line of sight condition, that's right. And we're going to say m underscore tree node list dot pushback, and we're going to push back the m underscore line of sight node. So that, notice what we're doing here. We're creating a new node, a line of sight node, and then we're pushing back the condition on top of this, all right? And this actually is not following this because line of sight is actually up here, all right? But we'll fix it later. For now, we'll put it up here. So the line of sight condition in this case is going to be the top of the node. That's what we're saying here, okay? Cool. If that's true, then we're going to set the radius node. Here's our radius node to a new radius condition. Here's our radius condition for a second. And we're going to add node. If I was going to put the radius node second, right, I'm going to add node. This is new. Adding node to the tree. The parent of the radius condition is going to be the line of sight condition, because I'm making, in this case, the line of sight condition first. So again, it's not exactly this. It's going to be this and this are going to be swapped. Okay, so has line of sight is going to be up here, and detection is going to be down here. Don't worry about that. We're going to fix this in the next lesson part. But I'm going to do this for now just to make it work. So line of sight node is going to be the parent node. The child node is going to be m underscore radius node, which I just defined. So radius node. And is it going to be to the left or the right? Well, it's going to be the left tree node, this one. So the radius node is going to sit to the left of the line of sight node, line of sight condition. Okay, so again, this has line of sight into the left, or making it the radius node. This radius node here is going to be down here. That's how we're just making it so that it's baked in this way. Okay, that's what it's going to do. And we're also going to add it to the tree list. So we're going to say m underscore tree node list dot pushback, and we're going to push the m underscore radius node to it. Okay. Next, we're going to add the close combat node. Close combat node is going to say it's going to be a new close combat condition, and we're going to say that we're going to add node m underscore the parent is going to be the line of sight condition, the line of sight node, and we're going to say that we're going to add the close combat node to it, and it's going to be the right subtree. Okay, so the right node. So again, now we have a different way of doing it, where we have the has line of sight at the top, radius on the left, and am I close to the right? So it's going to be almost like this so far. All right, that's what we're doing. We're defining the left side and the right side, and m underscore tree node list pushback, and we're going to push back the m underscore close combat node to the tree. So far we've made all of our conditions. Remember, there's 3 conditions. We pushed them all back. Now let's add the actions associated with those conditions, because these are going to be roots of the rest of the tree. So this one's going to have 2 children, and this one's going to have 2 children for a balanced tree. That's what we're doing here, making a binary balanced tree. So I have left node and right node. Let's take this action. So the first one is, I'm going to make a tree node type. We're going to call this the patrol node. And we're going to say, let's add node this in. We're going to say the parent is the radius node. So the radius node is going to be the left subtree. So this is part of the left subtree. And the child node is going to be an anonymous new patrol action, right? And we don't have patrol action, so let's add it in. There's our patrol action. So we can do that too. And we can say that this is the left subtree. So the tree node, we're going to dynamic cast the tree node as an action node, right? Because that's what it is. And we're going to say that the patrol node, right, even though it's a tree node, we're going to set the agent, right, to whatever the agent is that's pointing to this tree. So this decision tree. Because remember, the decision tree also keeps track of its own agent. That's what it does, right? And then we're going to push this to the tree node list. Tree node list dot pushback, and we're going to push back the patrol node. Okay. So that is the left tree of the radius node. Notice the radius node is the parent, and this is the left tree. Okay. So let's do it again. I'm going to copy paste this whole part. And instead of patrol node, let's do the next one. It'll be the move to line of sight node. That's what we'll call it. Move to line of sight. We'll still have the radius node as its parent, but we're going to make a new move to line of sight action, which is going to ask us to, if I spell it properly, it's going to ask me to include the move to line of sight.h, and it'll be the right tree node this time, right? So move to line of sight is going to be an action node. Oops, undo. Just renaming. And what it's going to be is the move to line of sight is going to be an action node. And it's going to also set its agent to whatever the agent is, just for, we're doing this because we want to keep track of the agent in each of the nodes. That's what we're doing here, right? And we're moving to line of sight node is the, we're going to push this onto the tree. So that's the left subtree. So this is left subtree, okay? And now we're going to do the right subtree. I'm just going to copy paste all this. So copy paste all this, and we'll just, so it's faster. And this will be the right subtree. Okay, so the right subtree. So the right subtree is going to have the, on the right side, we're going to have the move to player node. Move to player node. That's going to be one. And that'll be on the left side. And on the right side will be the move or the attack node. Attack node. Okay, so move to player node and attack node. Move to player node, the parent of this is going to be the close combat node, right? So close combat node is going to be the parent of both the move to player node and the attack node, okay? Here we're going to have a move to player action, move to player action. It's going to ask me to add that in as a new include, right? The move to player node is going to be added. The agent is going to be added to this, and the move to player node is going to be added to the tree. The attack node, right? You need the attack action, right? Which is what we want to do, a new attack action. There we go. That's going to be the right tree, and we're going to take the attack node and attach it there and there. And that is, for the most part, my tree. So what do we do different? So what we did different from a drawing perspective is the top of the tree is the line of sight node. So it's not this diagram. This diagram here that we're showing you, this is just an example of maybe one way of doing it, okay? But instead, what we've done is do it something different. Let's make a new, just in the PowerPoint, let's add that in and talk about what it would look like. So new slide. So if I was going to add that in, actually, you know what? I'm not going to do it here. It's just to save time because we're running out of time. We're already at 2:49, and we're kind of at the end. But more or less, what we see is that the root node is the line of sight node. To the left of the line of sight node is the radius node. To the right is a close combat node. So either am I in line of sight? No. Then am I in radius? No. Then patrol, because that's the first action I'm going to take. If everything is no, 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 then keep patrolling, right? Okay, how about this? Am I in line of sight? Yes. Okay, cool. Am I in close combat? No. So close combat, no, means I want to move to player. I'm too far away. That's how it would work, right? Okay. Am I in line of sight? Yes. Good. Am I in close combat? Yes. Then I want to attack. That's what it does here. So very, very simple way of doing stuff. It's not really complete, but it does accomplish a lot of the stuff that we have put together so far. So that is our decision tree. Let's put this up on GitHub because that's the last thing we're going to do for the decision tree. So git add dot, git commit minus M, and we'll say added decision tree .cpp now. CPP is complete. Git push. All right, so that is both the decision tree.h and the decision tree.cpp, those two pieces. Okay, now it tells you there's a couple things. It kind of underlines this, and it says here, it says insert no discard. I recommend we do that. Let's insert no discards in all these. This is for, again, modernized C++. It's not going to change functionality. It's going to take away warnings and a bunch of other stuff that we don't want in the compiler for C++ 17 and 20. Okay? So that's what those do. So that's the only thing that it gave us warnings are. The decision tree says it could be made into a, we can click a derive class. It also recommends things like for the decision tree itself to make it a leaf, or sorry, a final. We can mark it as final, so you can't inherit from it, but it's perfectly fine this way. All right, so now that we've got our decision tree, I know I'm running over time, guys, bear with me. Now that we've got our decision tree and we're done, we've done this piece. We've kind of done the, let me also close off this thing here just to give us more room, because we're not going to follow this diagram. This is just an example of how we would do it. Here, we're going to modify the placing.h and placing.cpp to add the decision tree to it. Because right now we haven't added it to it at all. We've made it, but we haven't done anything with it. Okay. And in future videos, what we're going to do is we're going to add the decision tree to the starship, not to the scene, not to the play scene, right? So it's part of each of the enemies, okay, that we're going to use. But now in this case, we only have one starship. We're just testing to see if the tree works. So that's why we're only going to add it to the play scene for today. Okay, it's the first step to test it. So let's test the tree up by adding it into the play scene.h. So under play scene.h, right, if you notice, we have a, we've set up a bunch of stuff already for you, right? And what we want to do is we want to include decision tree up here. So under the include, we're going to say, let's include decision tree.h in preparation. So this is new for lab 7, okay? We're adding in decision tree.h. And what I want to do, right? What I want to do is I also wanted to mention a couple things here for ship position and angle. We've kind of put that in there as well. I put those two, and angle and the ship position. I'm also going to, so I've added those things in to help us get through it. And at the bottom, you'll see that there's a to-do where we want to add in a decision tree pointer. So decision tree pointer M underscore decision tree, this one. Okay, so that's kind of what we did. So we did this. So now we added the decision tree in here. We can get rid of this decision tree. Notice it was blue before, and now it's not. Well, because I marked it as a to-do. Whenever we mark it as a to-do, we see it as blue. So this says decision tree has never been initialized. It's not used, blah, 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 right? We're going to come back to this in a second. Next, in the .cpp, it's going to this. So the placing.h is done. The only thing we've done is add a decision tree pointer right here, and we just included it up here just so we had it. Okay, these are the new pieces. The .cpp, we want to do kind of the same or similar things up here for what we're doing. So I'm going to go through the list here. Draw, we're not drawing anything different. Okay. Update, we're not doing anything different. All of this is, for the most part, the same, except for what we want to do is we want to make a decision with the decision tree every frame. So here in the update function, we want to make a decision. So every frame we're thinking about making a decision. So we're going to call the decision tree's decision, M underscore decision tree, and we're going to say make decision. Whatever the decision is going to be, that it's going to look at every frame. Okay, that's what the decision tree is going to do. Okay. Handle events isn't going to change. In our start method, let's go back all the way down to our start method here. So I'm going through keyboard events and build obstacle pools and build grids and all this other stuff. And we're scrolling down until, or we can just jump to the start method. Here's our start method. At the top, it says Lab 7 Part 1. We added our line of sight mode to the target and a bunch of other stuff. We set up our keyboard and mouse input. We have our background image. This is our background image, how we added it in, that image, that picture that we added in. We added in the target and the starship, as well as build obstacle pool. We did all that the same as we've done it before. We set up the grid, and now we need to set up the decision tree down here. This notice is a to-do, create decision tree here. Let's do that. So we're going to say create decision tree right before the music is being played and all that stuff. And we're going to say m_decision tree is equal to a new decision tree. And we're going to pass in the m_p starship as the agent that we're going to connect the decision tree to. So we're using here, using our overloaded constructor for the decision tree. So we can set the starship here. We're also going to display the decision tree, how it's been created. This is really optional. It's really for us just to see what the decision tree looks like. And _decision tree, we're going to make a decision for the first time before we start in the update function. So make decision is going to start us off most likely in patrol. Okay, that's what it's going to be, patrol mode. Here, we're going to preload our sounds and our music, and we're also going to play the music here, and we're going to call the IMGUI window function. Okay, that's what it's going to do. So for now, we've just done this part. So we've done this right here, and right now it's going to stay in patrol mode, but the starship hasn't been coded to do that. Okay, let's play it and make sure that it works. Remember, if it doesn't, this is the time to fix it, because if we go further than this, the decision tree is actually going to be tested right now if there's an issue. And we're going to wait for this to load, and hopefully it's not going to give us any errors. If it does, we'll fix them. Hey, look at this. Okay, so the scene was activated. As an example, look what it says. Patrol action, move to line of sight action, patrol action, attack action, performing patrol action. Okay, so I want you to think about why this is saying the stuff it's saying. Remember we said build or display the tree, right? So, what did we get wrong here? Well, most likely something's named improperly. Let's think about this, right? So if I go back to, because that's not displaying right. The display actually helps us with the tree naming. So stop. Let's take a look at the actions. So we had an issue. Maybe it was me, my bad. Let's take a look at the, so we have conditions. Let's take a look at the line of sight condition. So line of sight condition says, this is the line of sight condition that gets loaded in. So that's the first thing. So line of sight, okay? And then from the line of sight condition, it says, do I have line of sight? The answer is no. So then I should go to the radius condition. So radius condition's here. It says radius condition. Okay, that's the radius condition. And then, okay, do I have, do I detect the player? No. So I'm not in radius, not in everything. I'm going to go do the patrol action. So patrol action is what I'm going to have, and it's going to say, it's going to go patrol action, performing the patrol action. That's what it's going to do, which is really what it said first. That's what it said, kind of performing the patrol action. Okay. But let's see what it did. Let's see what it actually did when it came to displaying the function. So in our tree itself, so if I go back to our core, and if I look at our tree, decision tree.cpp, what does display do? Remember display? It just displays the entire tree node list from the top to the bottom, right? The way things have been added. That's what this does. So it says for every node in the tree node list, I want to output its name. For every tree node in the tree node list, output its name. Well, that's weird, because in here, let's make sure we've added it properly. We've added a line of sight node, a radius node, a close combat node. We've added in a patrol action, a move to line of sight action, and we've added all those things in. Make sure look at these. You can see that these are all things we're pushing back to the tree node list, right? Attack node, move to player node, move to line of sight node, player patrol node. We're adding all those in, right? And we're making brand new actions. So these are all been added into the left and right tree nodes of everything else. These things are correct. Close combat node is the root, right? As an example. And so we can see what this looks like, okay? So that's interesting that it didn't do what I expected it to do. I expected it to, when it was displaying in the display function, it was going to display all the nodes. Okay, so that's weird. Let's try that again. So if I go it again, you can see what it does is, and you can see here, so I'm just going to open this up for you. So, okay, so it says obstacle, obstacle. Okay, so here is what I missed, because it actually had it here. Here's line of sight condition, radius condition, close combat condition, patrol action on the left of the radius condition, move to line of sight action on the right of the radius condition, and then it says patrol action and attack action. So those two actions, patrol action and attack action, it says the same thing, but patrol action, it shouldn't say patrol, it should say move to player. So maybe we did that wrong. Let's try that again. So going to actions, that's why I was confused. Move to player action, CPP. Look at that, there it is, there's the problem, right? So it just is named incorrectly. This should say move to player action, right? I just didn't name this properly. I know Yigit was very good on, hey man, you didn't rename your actions, and I didn't. See, this is the problem that I had, right? So make sure they're named properly. So let's go to the CPP. So CPP attack action, CPP for move to line of sight action, CPP for move to player action. That's good, now it's fixed. CPP for patrol action, right? And that's all the actions. Let's go to the conditions. So CPP for close combat condition, right? CPP for line of sight condition, CPP for radius condition. All the conditions are correct as well. Good. Let's run it one more time, and we should see the proper order of things. So now, line of sight condition, radius, close combat, patrol, move to line of sight, move to player, attack. So that is a tree right there. And if you really want to point this out nicely, because we really don't have anything, it's just a little diagnostic that we just did on if the tree is set up correctly. Let's take a look at the core for decision tree, and let's modify our display function so it says that. So it says, so this is the decision tree. So standard cout. Let's say something like decision tree nodes, right? And then we can make some kind of fancy dancy thing. Add in a couple of a line that goes like this, just so that we can see that this is special. There we go, and we can close it off too. We'll do one of those here and one of those here. We can see these are the tree nodes, right? For this and this. So this is all the tree nodes. Let's run it, and you can see that now that I've added in just this part, it's going to basically display stuff properly. So there's the tree nodes. Okay. But now it says performing the patrol action. It's performing the patrol action because it doesn't have line of sight. Take a look at that. But it's not really moving anywhere. It's not moving anywhere because you know we haven't programmed the ship to do any of that. Michael says sorry for not reacting. Had an audio issue. Was following the YouTube version behind. No problem. No problem. All right. So that is the display. That's pretty cool. We've added our decision tree to the placing. Let's put that up on GitHub. So I'm going to say git add dot git commit -m, and we'll say added decision tree to placing. Git push. So that's what it did. It kind of did all that, and it fixed some of the problems we had when displaying the thing. So Fabian, check your CPPs. If it says all the same thing, it's because it's a copy pasting error. Should be anyway. All right, cool. So that is the decision, and we're making a we're playing a specific action, right? So that's the one thing to do. But now what we need to do, we've kind of come down to the last part, which is this piece, which is changing our starship, and then we're done for the day. I know I'm running overtime, but it's a bit of a longer setup for the lab today so that we can get things done. So starship.h, I want to add a vector for patrol and waypoint index. Let's do that. So in the starship.h, I'm going to go to the agents. I'm going to go to starship.h, and under our starship.h, so here we have our functions, get max speed, set max speed, getters and setters, our seek and look where we're going, and maybe a reset function. And, again, down in here, we have our max speed, our turn rate, our desired velocity, and a bunch of other stuff here. Well, new for this piece, before we get into these functions down here, so we're going to say new for lab 7, right, is a standard vector of type GLM vec2s, which we're going to call the patrol path. Okay, that's the patrol path. And we also want a waypoint that we're going to use here. Okay, so the vector, patrol path, and waypoint. Okay. And we're setting this up so we can follow along, follow the a set of waypoints that we're going to put together. Okay. Save. And now in the spaceship.cpp, what we want to do is we want to set some of this stuff up, right? So again, all we've done is we've created a vector of a vector of vec2s. Vec2s are vectors, like X and Y coordinates, right? And that's the vector path, the patrol path. We need to build this up. We need to build up the patrol path, right? So it'd be nice if we had some kind of method to do that. So let's do that. We'll make a private method called, build patrol path or something like that. So build patrol path. And that private method is where we're going to actually do the work to build the patrol path itself. Okay. So let's do that. So we'll go here and we'll generate a definition for that here. Build patrol path. And how does the patrol path work? The patrol path is basically going to set up our the path that we want to patrol around. Okay, so let's set it up. So remember that patrol path is a vector that's empty. We want to add stuff to it. So we're going to say m_patrol path dot pushback, and I want to add in a GLM vec2 object. And let's say that the top right corner of the screen is something like 760. This is just a node, if you trust me, 760 by 40, just to save time. That's the top right, top right corner node of the screen. That's what that is. That's the first patrol path, the first node, if you will. And I'm going to do the same thing for the next one, which is I want to push back a new GLM vec2 for the bottom right. So top right, I'm going to go to bottom right, bottom right corner node. And the bottom right is 760, and I think it's 560 for the bottom right. And let's do the same thing. Very simple patrol path. I'm going to push back the bottom left corner. So bottom left is 40 and 560. So 40 would be the middle of the leftmost node, right? And finally, the top left, right, which is going to be 40 and 40. Okay, so that's the patrol path that it's going to take. It's going to go around the screen. And by default, I'm also going to set up my waypoint to 0. So that is the first, it's going to that's going to be the way I'm going to iterate from one, patrol path to the next, right? What I want to do here is I'm going to set my target position to the m_patrol path for the first time, and I'm going to pass in the m_waypoint, which is 0. Okay, so this is going to start at the top right corner of the screen to start. That's the first place I'm going to go to. Okay, I'm going to use a waypoint to get there. And I'm going to iterate, I'm going to update that waypoint every single time. So waypoint 0 means this is this one. Waypoint 1 means this one. Waypoint 2 means this one. Waypoint 3 means this one. And then I want to go back to waypoint 1 again, or waypoint 0. I want to keep on going from one point to the other. So that is building the patrol path from the initial time we're going to do that. And what I want to do is I want to take this little build patrol path and call it in the constructor function, which is just going to be called the Starship constructor function right here. Before I set the type, or even after I set the type, it doesn't really matter. I want to build the patrol path. Builds patrol path. So that's what that just did. So we added path to it, and we just build it up. So a couple things just to set some stuff up here so it works a little nicer. So rigid body, right? Again, what we've set up here is our velocity and the acceleration. 0 is colliding is false. We also have a current heading that's 0. Our line of sight distance is 400. That's still set up as last time. And our whisker angle, if we had more whiskers, it'd be 45 degrees. We're not really using that right now. Our line of sight color is set up as a default red by default. And here's something else we need to do. We need to set up our action state by default. So our action state is what I'm going to do down here. So I'm going to say set action state, because remember we added our action state to our agent. We're going to set that up as a default action, which is no action. So we're not taking any action yet by default. And what we want to do is when things have changed, then, so this is new. I'll say this is, again, new for Lab 7. New for Lab 7, okay, in here. And new for Lab 7 is the stuff we're adding. We're adding a set action state, and we're also building the patrol path, okay? Nice. So that is the first part. So draw functions, no problem, it's same. And we draw a line for the line of sight function. That's what we're doing there. We have our update function, and our update is where we're going to do the decision. So let's get rid of this part. We're not going to do move and check bounds yet. Instead, what we're going to do is we're going to determine, right, which action to perform based on our action state. So we're going to switch on our action state, right? And we're going to say case, what's our first action? The patrol action, right? So action state is interesting because action state is what I want to do, but it's get action state is what I want to use. And I can say that there's a bunch of stuff. The only thing is I want to react to right now is the patrol action. So if it's patrol, then what do I do? Because I don't have any actions yet. I haven't really defined anything else. Today, all we care about is making things move around, the patrol action. So we're going to say m_move, right? The move action that we want to take. So we want to move the ship around. All right, that's what we're going to do. And that's the only action that we're going to take if the action state is patrol. If the action state is patrol, which we're going to switch to in a second. All right. So what does the move action do? What does the move action do? Well, if we go back, right, and take a look at what the move action does, it seeks. And it uses our formula to move around the scene based on our kinematic equation that we're going to learn more about in the fall semester. All right, so that's what it's going to do here. We're going to use the kinematic equation to move. Nice. And well, how do we seek? So here's the seek method. And right now, the way it's seeking is it's setting the desired velocity, and we're using the steering direction to move. We're using steering behaviors here to move our ship around. But what we want to do here is we want to find the next waypoint. So let's find the next waypoint to move the ship around, right? And the way to do that is if util distance, if the distance between my patrol path and the current waypoint, m underscore waypoint, if the distance between there, which is a vector2 object, and our get transform dot position, if let's say if this is less than 10 pixels, so again, what this checks is find next waypoint if within 10 pixels of the current waypoint. Right, what's the next waypoint we have to go to? Then we can say that check to see if you are at the last point in the path, because if we're on the last point in the path, we want to go back to the 0th point. So if, and we're going to say plus plus m underscore waypoint, we're going to increment the waypoint right away. So we're going to go from 0 to 1. If that is equal to the m underscore waypoint, patrol path dot size. So if we're at the last waypoint, right, then set the waypoint to 0. So if so, then we want to reset. So we're going to say that m underscore waypoint is back to 0. So this way it loops from 0 to 3 and then back to 0 again. And then finally, we're going to set target position, the target position to m underscore patrol path, m underscore waypoint. So this is using the stuff we already have. This is stuff, the steering behaviors, the steering behaviors we already have. We're adding it in so that way we can patrol around the scene. Now, there's a little funny thing here that says that we want to, it might be a good idea to negate the expression. I'm not going to do that here. Save. And if everything goes well, guys, then it's going to make a decision. It's going to set the action of my starship. It's going to set it to patrol, right? And the way we know that is because starships are agents, right? Starship are agents, and because we updated the agent itself so that we can get action state and set action state from the very beginning, we can store an action state, a current action state in the starship itself, and therefore we'll know what state we're in: patrol, attack, move, whatever we're doing, okay? Here we're only in the patrol state, and that's the only thing we care about because we haven't set up the other ones yet in the update method. So if you look at the update method, the only thing we care about right now is the patrol action. So that's why we're moving. We're actually going to take the action that the patrol, that's what the patrol action is, move. We're moving around, right? And if we had other actions, we could do other cases here. Like for example, if I had line of sight, then maybe I could shoot, right? As an example. So let's say case our action state was if we attack, right, then we could perform the attack action, whatever that is, perform attack action, right? If we had that. We don't have that right now because we didn't define what that attack action is. That's going to happen another time. And I could also have a case where I want to do the move to line of sight, and this would be again something like perform move to line of sight action, whatever that is, right? How we're going to do that, we're probably going to steer there wherever the closest node is to give us line of sight, right, as an example, and so on. I'm not going to do the rest. All right, but that's the idea here in our update function. Okay, let's see if this works. So let's run it. And if everything goes well, then we should have our ship moving around. Maybe, maybe not. We'll see, and we'll troubleshoot the problems if we have any. I know I'm running overtime, guys. Bear with me. But this is the first part of lab 7.1. So notice it goes here, and then once it gets to the last node, it should turn, right? Hey, look at that. And it's turning down the screen, and it's going to go to the last node down there, right? So if you notice what it looks like, if we put the grid on, it looks like this. It goes to the last node, and it keeps going, right? And it's going to go around the screen because you can see that it doesn't care, right? Notice that it's changing the angle until it gets to the corner and then goes up. So that's the patrol. And why? Because we're in patrol mode. We're in patrol mode. So we can switch this, as an example. If the ship has line of sight, we can switch it to stop, right? And that's what we're going to do next week. So that's it for this week, guys. Question? And you can enjoy the music too. Questions? Let's put this up on GitHub then. So let's do this. So say clear git add dot git commit -m, and we'll say kind of a modified starship to patrol git push. And that's really it for lab 7.1. All right, so lab 7.1 again is the first piece. Hopefully you found this useful and instructive. And the reason for this is we did a lot of work today, a lot of setup for next week. Today we did pretty much everything we needed to do to set up our decision tree, which is pretty awesome. Okay, questions? Any questions at all? If you don't have any questions, that's fine. I'll ask this question for you guys. Are you with me? Check mark if you actually you completed everything to set up, because guys, you're going to need this. Good, that's good, that's good, that's good. Fabian, hopefully you can respond now. Ali, Abu, because guys, this is the setup. This is where you're going to start, right, for your lab 7.2, which we're going to start off next week. Okay. Fabian can see the seek function. Sure, no problem. So the seek function is, let's just go jump to seek. Here's the seek function right here. So again, this is kind of an interesting way of iterating. We're iterating through, we're going to the next waypoint when we're within 10 pixels of the current one. Whatever the current destination is that's when we're going to actually update the waypoint. We're going to change the waypoint when we're pretty close. If we change this number to something closer like 5, it's going to seek, it might go out of bounds actually. That's why we made it that. Okay, guys, hopefully this was good, and hopefully you've got everything, Fabian. That's it for me for today. But before we go, one thing to note is I want to bring up a couple of things. This is all the stuff we did today. But just to point out for Thursday, and I'll reiterate this on Thursday, remember that this lab, we build the lab over several days together. It's not something that we're going to build up and going to submit on Sunday. All right, that's number one. Remember that assignment 3 is due this Sunday. Assignment 3, you've had some time to put things together for your animations and so on. If you haven't done so already, please sign up for groups of up to 3 members for assignment groups A3, 4, 5. If you don't do this, assignment 3 will be a dud. You won't be able to submit it. And you can't do assignment 4 without a done assignment 3. So please make sure you combine with somebody as soon as possible. Work on it as soon as you can. Meet with your team and get it done for Sunday. Again, this assignment is worth 10% of your final grade. So it's pretty serious, just like all the other things are. But please don't forget to start this if you haven't had a chance to. When we meet on Thursday this week, it'll be about behavior trees. And that's it for me for today. I'll stop recording this and take any questions. Abu, if you want to stick around, we can talk about what I need to do with you. Okay, that's it for me. I'm just going to stop recording here on YouTube. Take care. Okay.